In section 2.5, we're going to be looking at evaluating limits algebraically. Up to this point, we have used graphical, numerical, and substitution to determine the value of a limit. Now, substitution you might not remember because basically substitution means just plugging in a number and seeing what we get out. Now, if we get out something that's reasonable like a constant, I'm done. If I get out something unreasonable like infinity or 0 in the denominator, it means I need to look further into it. But so far, we've used these three approaches. Let's go ahead and look at a graph starting out with f of x equals x squared minus 4 all over x minus 2. Now if we were to look at this graphically in Maple, let's see what we'd get. So here's the graph for Maple. Now what Maple doesn't know, or is not considering, is this denominator x minus 2, this means x cannot equal positive 2. So that means if we plug a positive 2 in here, we should actually have a hollow point here. But Maple doesn't realize that. So this is not a continuous line. There's a discontinuity at 2. Maple doesn't realize that. So let's go ahead and look at the limit as x approaches 2 of this function. Limit as x approaches 2 of x squared minus 4 over x minus 2. Well, let's go ahead and look at this graphically. Using the graph above, we can see that the limit as x approaches 2 from the left of this function is equal to the limit as x approaches 2 from the right of this function, and that they are both equal to 4. And because the limit from the right equals the limit from the left, that tells me that the overall limit exists. So therefore, the limit as x approaches 2 of this function is equal to 4, because the limit from the left and the limit from the right are equal. So there's kind of a graphical approach to this, and there's my solution. Let's go ahead and look at the same problem using a numerical approach. So let's look at the limit as x approaches 2, same function, x squared minus 4 over x minus 2. Now, using the numerical approach, this is where we need a table of values. And from this table of values, what we want to do is we want to choose values that approach 2 from the right and from the left and get very, very close to 2, but we can never quite equal 2 because we know if we plug 2 in, we get undefined. So we're trying to see what's occurring or approaching on either side. So these are just some arbitrary values I chose. You could have chosen other ones, but it is nice to get very, very quickly close to 2. You know, we don't want to start here, let's say, at negative 10 and then move up toward 2. That wouldn't make sense. Or start at positive 10 and move down toward 2. We want to get very, very close to 2 very quickly. So what we do is we take this value of 1.9, we plug it into this expression and see what we get back out. And then when we do that, we get 3.9. We get 3.99 and 3.999. Well, it kind of looks like to me the limit as x approaches 2 from the right of this function looks to be approaching 4. And instead of using equal here, I'm going to put approaches 4. Now on the left, let's see what we get. Here, let's start with 2.01. I get 4.01, 4.001, and 4.0001. So it looks like here the limit as x approaches 2 from the right of my function x squared minus 4 over x minus 2, it approaches 4 as well. I'm going to kind of move this around a little bit. We're going to use our approach arrow from this direction. So this approaches 4 as well. And as I'm looking right here, I should have approached this one from the left. So I'm making a quick change to the left here. It did say to the right, and this is from the left. So on the left, I have the limit as x approaches 2 from the left of the function is 4. It approaches 4, as you can see. From the right, the limit as x approaches 2 from the right approaches 4. Therefore, because these are equal, the limit as x approaches 2 of my function is equal to 4. The limit is 4. The functional value is not 4. The limit is 4. So there's the graphical approach, there's the numerical approach, and then of course we talked about substitution as well. So the limit as x approaches 2, x squared minus 4 over x minus 2. Substitution just says plug it in and see what happens. So if we plug this in, we get 0 over 0. And 0 over 0 means, here we are, indeterminate. And indeterminate means to do more work. Now the more work that we can do are graphical and numerical, and today we're going to add one more to that, and that's called the algebraic approach to solving for limits. So let's go ahead and look at the algebraic approach. So this is kind of our new introduction, and we've actually done this already. We've used it quite a bit, but we'll add some more tools to the box here on this one. So the algebraic approach says, let's try and rewrite this. Let's try and get this into a form that I can work with. So the first thing that you might want to note is x squared minus 4 factors. And because x squared minus 4 factors, that might be an idea that we can take this and rewrite it algebraically. Now, one thing we don't want to do is to drop this limit notation. So keep this in mind. Do not drop the limit notation. If you have not taken your limit yet, I expect to see it rewritten until the limit is taken. X squared minus 4 factors into x plus 2x minus 2, the difference of perfect squares, over the quantity x minus 2. And of course we can cancel factors. This is equal to the limit as x approaches 2 of x plus 2. Plugging directly in, we get 4. So out of those different methods that we used here, it looks like to me that algebraic is probably the easiest approach. Numerical is certainly computationally heavy. Graphical is not too bad as long as it's an easy graph to use, but algebraic approach looks pretty good here. So let's go ahead and talk a little bit more about these indeterminate forms. The indeterminate forms that we've already talked about are 0 over 0 and infinity over infinity. So again, we've looked at these a little bit before, and when we get these we say do more work. Well, there's other indeterminate forms as well. For instance, infinity times 0 is indeterminate. Infinity minus infinity is indeterminate. And we also have some others that we'll get to in Calc 2 that involve transcendental functions. But for now, these are the indeterminate forms that we typically look at. Now again, we've talked about these and we said do more work. Well, the same is the result for here. When I have these indeterminate forms, that also means to do more work. Okay, but these are kind of the ones over here on the left are the ones that we're used to working with. So let's go ahead and look at some of these indeterminate forms and see how we can work with them. Okay, let's go ahead and look at a limit that involves some trig functions. Let's look at the limit as theta approaches pi over 2 of secant theta over tangent theta. So let's go ahead and plug directly in first. If I plug directly in, so we can evaluate this limit by plugging directly in. So I get the secant of pi over 2 over the tangent of pi over 2. Evaluating here, the secant of pi over 2 is actually undefined. It's 1 over 0. And remember, secant is 1 over cosine. The cosine of pi over 2 is 0. Tangent of pi over 2 is the same as the sine of pi over 2 over the cosine of pi over 2. So I get 1 over 0 divided by 1 over 0. Now at this point you don't want to say anything divided by itself is 1 because these fractions are undefined. So this is indeterminate. Indeterminate means to do more work. Well, this is the algebraic approach. We could graph this. We could look at this in a table numerically, but we want to look at the algebraic approach. So the algebraic approach says to try and rewrite this somehow. Now this is not a nice algebraic expression that we can factor and cancel. Whoops, this is theta approaches pi over 2. So we're going to have to look at this in terms of trig functions in rewriting here. Secant is 1 over cosine, tangent is sine over cosine. And of course, when you divide by a fraction, you multiply by the reciprocals. Now something I'd like you to keep in mind is you should always put parentheses around the arguments of your trig functions. So I have 1 over cosine theta. The denominator flips and I'm left with cosine theta over sine theta. Of course, the cosine thetas cancel, and I'm left with the limit as theta approaches pi over 2 of 1 over sine theta. Whoops, 1 over sine theta. Now I can just go ahead and take that limit. I'll plug directly in using substitution, and I have 1 over the sine of pi over 2. The sine of pi over 2 is 1. 1 over 1 is 1. So my limiting value is 1, and that was easily found algebraically using some basic trig identities to rewrite my trig functions. Let's look at another one. The limit as x approaches 16 of the square root of x minus 4 over x minus 16. So this one we can plug directly in as well. So plugging directly in, I get the square root of 16, which is 4 minus 4 over 16 minus 16, which of course is 0 over 0. 0 over 0 represents an indeterminate limit. An indeterminate means to do more work. Well, the more work we can do here is algebraic. So the first thing that we could look at is the limit as x approaches 16, and look at this in terms of factoring. Now the denominator does not look like the difference of perfect squares, but we can actually rewrite it as the difference of perfect squares using a radical notation. And of course the root x minus 4's cancel, and I'm left with the limit as x approaches 16 of 1 over the square root of x plus 4. And of course the square root of x would be square root of 16 plus 4, 1 over 4 plus 4, which is 1/8. So that limit equals 1/8. Now, just because you get indeterminate, that doesn't always mean that your answer will be equal to 1/8 or anything that we can depend upon. So that's why indeterminate means you need to do more work. Now let's do the same problem, but with a little bit different approach. This is still going to be an algebraic approach, but this is just another algebraic approach that we could use, and it's called multiplying by the conjugate. So again, we start with our original problem, square root of x minus 4 over x minus 16. Now if you look at this, we might be able to clear out the fraction if we multiply by the conjugate. So the conjugate that I'm looking of is a conjugate of the numerator. Now of course the conjugate means that we just change the sign that are between the terms of the binomial. So the square root of x has stayed the same, the 4 stays the same, but what we need to change is the plus. So what I have now when I multiply this out is I have the difference of perfect squares now that will come out in the numerator. So I end up with x minus 16 in the numerator. The denominator ends up with, actually we're approaching 16, I forgot to fill that in. In the denominator we have root x plus 4 times the quantity x minus 16. Now what cancels are my x minus 16s. So here we have the limit as x approaches 16 of 1 over the square root of x plus 4. And then this should look kind of familiar. That kind of picks us up right in the same spot, and so we end up with 1/8 again.